first lecture of the chapter which is, you can say, important one and which is a little bit difficult one also. The name of the chapter is System of Particles and Rotation. In this particular chapter, we are going to talk about important topics. For example, rigid body, what it is, center of mass, motion of center of mass, torque, angular momentum, then rotation, then rolling, then pure rotation, and all together. You can say moment of inertia, theorem of moment of inertia. Okay, so this is one of the important chapter in the first book of class 11. Then after that, we have a you can say totally separated, or you can say the subtopics we are going to learn in the next chapter, which is gravitation. That is not belong to the previous anything, but that is belong to the previous thing. So what is rigid body, center of mass? We are going to learn in this particular chapter, sorry, in this particular class, today's class. And moreover, we are going to learn also the motion of center of mass. Center of mass for continuous things, center of mass for non-continuous, or you can say center of mass for discrete objects or bodies, center of mass for rigid, continuous bodies. Okay, so that is important one. And every year, at least one question from this particular chapter you are going to see in any entrance exam. Suppose you are going to give 4 or 3 or 3-4 exams. For example, CUET or any particular entrance exam in JEE level or NEET level. So at least one of the questions you are going to face from this subtopic. Okay, one of the most important. So basically, rigid body, what it is. Every particular body is a rigid body. This is just a basic example. For example, till now in the previous chapters we learned this is. What is this? Mass particle, or you can say point mass particle. Point mass particle. Okay. But what a rigid body is, every, you can say, body in our surrounding is a rigid body. As you can see, this whole body, if I'm talking about this, the first skeleton type structure, this first skeleton type of structure. Okay. So this is made up of so number of different small components. This. Clear? Even these small components, if I just took a head in this particular, suppose this is the head. Okay. This is the head. So even this head is also made up of n number of point mass particles. And these n number of point mass particles are equidistant from each other. If I'm zooming this a little bit more, so what it is, they are fixed, and the distance between these 2 point objects, or you can say 2 point mass particles, is going to be remain fixed. This is not going to change. Okay, I mean the distance between the 2 particles, once it is going to be established, it is going to be fixed. Is it clear? Yes, R or this R prime is going to be changed maybe, but whenever it is going to be fixed, this particle, if I am fixing this particle 1, 2, 3, 4, so that is going to be 1, 2, that is going to be 2, 3, and that is going to be R3, 4. But R3, 4, R2, 3, R1, 2 is going to be fixed. Is this clear, beta? So that is all about your rigid body. We are going to, I'm going to define properly what rigid body is in the next slide. But first get the feel of a rigid body. Means up till now, we learn and everything in this particular manner like this. This is the point mass particle. Okay. Very minute. Clear? Very minute. Minute means very, very small. Small in size, very minute, and that is known as point mass particle. So whatever we learn, acceleration, force, displacement, torque, or you can say not torque, but this momentum, and you can say frictional force and tension force and any particular kind of force or everything up till now, okay, in the physics we learn for this point mass particle. But in day-to-day life we know we have a rigid bodies. Clear? We don't have this point mass bodies which are made up of with the components, and these even smaller components are made up of n number of different these point mass particles. So if we are going to discuss, why we take this concept, what is this center of mass and why we taking this, just a little brief about it. There are two options. Either we evaluate any particular new concept, that is center of mass, or the another thing, the previous thing, or we can do one thing, we can find everything for this particular single particle, for this particular single particle, for this particular, for this particular, for this, and we can do the summation, isn't it? But when we are doing this summation and when we are doing this mathematics, so that is very problematic, even that is troublesome, because even I am not taking the whole body here, I am just giving you a brief thing or brief introduction about the head only, and you can say and you can find the shape of the head is different from the shape of the legs or even the arms. So we have different particles, different kinds of a body, symmetric, unsymmetric, and when we are going to do the statistics is basically the whole mathematics or whole summation, even with the help of integration or even with the help of this summation, I equals to 1 to n. If I am just finding total force, so that is going to be very troublesome. Why so it is going to be troublesome? Because even the smaller components have millions, or you can say up to the level of 10 to the power 4 or 5 level particles. Okay, so even if I'm trying to do that, that is going to be a very difficult or a kind of a impossible task. So that is why we evolve this center of mass. So first of all, we're going to learn about rigid bodies and what is going to be happen when we apply a force, or you can say when we try to find the, you can say the futuristic thing. Futuristic means when we apply the force, so how these rigid bodies going to be behave. So we are going to find this, and then how we are going to find any particular point which is a frame of reference, or you can say the motion of that particular point or the acceleration of that particular point. Clear? Okay. So the next thing is the definition of a rigid body. So basically the definition of a rigid body: system of particles which does not change its shape under the influence of ordinary external force, and distance between them, the particles, does not change with respect to them. Very simple. Take an example. Suppose there is this is a stone. Stone is a rigid body, right? Just for the simplicity, I make this particular stone with these much number of particles. What I'm saying, this is 1. Okay, you can even say 1, 2. This is fixed. Okay, so as you can see, I make this particular stone with 1, 2, 3, 4, 5, 6, 7, 8, 9, even with the help of 9 particles. So what is a rigid body? Rigid body is a kind of a body in which if I apply the force, okay, means if I apply ordinarily external force, this is F external, so the shape and size of this particular body or the distance between these two subparticles is not going to change. I can make extra also. I can make here. But to make it simple, I make lesser number of particles. Clear? It can be fulfilled, and it's my, it is just the simplistic version to make you understand more. So what is going on here? System of particles which does not change its shape means this particular system of particle, it is not going to change its shape under the influence of ordinary. Ordinary means easy, or not easy. Ordinary means nominal. If I apply huge amount of force, so obviously the stone is going to be break. Okay, the stone is going to be break even in the smaller particles. Very simple example of this: chalk. Whenever we write on a blackboard or on a green board with the chalk, so chalk is somehow this, not this, somehow a cylindrical shape, okay, or you can say this rectangular shape also. But if we apply a huge amount of force, or if we put that particular chalk into the water, so it is going to be distributed into the powder form. It is going to be break, and that is going to be happen with any particular rigid body. Take a phone of yours and boom, so it is going to be break into the components. Even that particular phone, don't do this. Okay, because obviously if you have some phone which is not going to work it out, or something which is not of use of yours, so you can try that. So that particular thing or object is going to be broken into the pieces, but even the smaller component, you cannot find this particular thing, the particles level or point mass particle level. Okay, and then you apply any particular force on this, so either it is going to displace completely, or either it is going to rotate. So displacement we done in the previous chapters. We are going to find the rotation effect. Means if I apply a force on this particular stone, got it? So obviously it is not going to change the shape, or neither the displace, so it is going to roll, or it is going to rotate. Okay, means hypothetically I can say that there is an axis, and we are going to see there is an axis for all rigid bodies. So what is going to be, when I apply the force, so it is going to rotate in this manner and shifted here at a little bit. Okay, so from this particular position A to particular position B, it is going to be moved even with the rolling. Rolling means the translational or rotational motion altogether. Clear na? So if you apply an external force which is ordinary, so it is not going to break, it is going to rotate. And that is we going to learn, and that is we going to see in the next classes. Clear? Good. So no body in universe is perfectly rigid. Okay, first of all. However, the bodies in which strain effect is quite negligible under the influence of external force may be said to be rigid bodies. Example, earth, billiard ball, etc. What is the strain effect? The strain effect is basically whenever any particular body is change its shape easily. For example, spring regain its shape. If you compress or if you extend, so it's change its initial shape to initial shape to final shape, and then regain its shape. So basically, strain, this particular word, strain is nothing but change in length divided by the original length. We are going to see in the next, the properties of matter, or you can say properties of solid matter, we are going to see there. Strain, three types of strain, Hooke's law, modulus, and so and so. Okay, so any particular object in which strain is quite negligible, we can say that is a perfectly elastic, perfectly rigid body. But any particular body in the universe is not going to be perfectly rigid. Okay, we take earth or a billiard ball, because billiard ball or earth are very heavy, or you can say very rigid. Even you apply a huge amount of force, so they are going to rotate. They are not going to break into the pieces. First thing, okay, important. Second thing, the internal structure of a rigid body and its shape and size do not change in the state of motion. So that is important also. Whenever you apply a force on any particular rigid body, so it is not going to change its shape either. It is not going to change its size either. Whenever it is going to be in the motion, or you can say in the state of motion. So in the state of motion, either it is the pure rotation, either it is the combination of translation plus rotation, which is rolling motion. Clear? Okay. Now the next thing, what we are going to see, how it is going to affect when we apply the force. So that is basically we are going to learn about a little bit about a rotation. So this is axis of rotation. Rotatory motion means motion in a rigid body. Whenever you apply an external force, so basically the motion in a rigid body is going to be the rotatory motion. So what is a rotatory motion? First of all about a body rotating about a fixed axis, then every particle of the body moves in a circle and the center of all these circles lie at an axis of rotation. So that is rotatory motion. Clear? What I am saying, suppose this is the rigid body, this unsymmetric shape. So if I am going to apply a force over here, so this is going to be rotated in this manner. Clear? In this manner. But obviously, from which particular axis and from along with which axis it is going to rotate, I need to make that axis. And that particular axis is generally or majorly or maximum number of times is going to be passes through center of mass. So what is the center of mass? What is all about? We are going to see in the next slide. Clear? So see, there are three things going to be done. If you apply a force, so either it is going to break into the pieces, either the shape of the object is going to be changed, means the distance between the minute particles is going to be changed, and that is how the shape of the change. And if the two of the things are not going to be done, so the third thing is going to be done, that is going to start rotating. Simple. Okay. So in rigid bodies, the initial two things are not going to be done. So the third thing is going to be done, that is, it is going to start the rotatory motion. And what is rotatory motion? A body rotating about a fixed axis, then every particle of the body moves in a circle, and the center of all the circles lie at the axis. Means if I make another circle even, I need to change the color. If I make another circle even, so that particular circle have the center over there also. Oh, clear? If I make a little bit more larger circle, so this circle also have this particular same center. Okay. Even not the same center, but the any particular point which is going to be lie on the axis. The center is going to be lie on the axis. That is the main thing. Clear na? Okay. So that is your rotatory motion. So Vi, the velocity of the ith particle of the of mass Mi, and Ri, the position vector of ith particle. This Ri and Mi basically this, and Ri, the perpendicular distance of the ith particle from the axis of the rotation. Suppose you pick any particular mass particle over on the second circle, so that is going to be, if it is the origin, okay, wait, if I take this particular thing is the origin, so that is going to be O, I can take this point P, that is P, RP, the distance from the origin, and the point P have a mass MP, and from there the perpendicular distance, it is going to be what? This R of P. Instead of I, you can change any another this subscript. This is clear? Clear now everyone what I am saying? Okay. Good. So now this is motion in rigid body. All the particles of the rigid body moves with the same angular velocity omega, larger I, larger Vi, lesser Ri, lesser Vi. Okay. One thing I am not teaching you again here. The next thing is center of mass. See, you guys know in the previous class I teach you this thing. Omega. What is omega? Angular velocity. Okay. Omega is angular velocity, that is d theta by dt. Theta equals to RL, if I am not wrong, right? Is this clear now? Where R is the radius. Arc of the radius is theta equals to R by L. No, that is correct. Length of R equals to theta by R. Wait, tan theta equals to theta, and that is L by R. I think I make this not correct thing. How you can find this relation? If I make very small theta, so tan theta, which is length of arc L, and that is radius perpendicular. So theta is going to be L by R. That is the correct. Okay. what I'm doing is, give me a minute, I'll explain to you guys. See, there is a relation between, suppose this is your, what? In this way you're going to understand. Suppose this is your circle. Okay, in this circle, this is the origin. The radius is going to be fixed. Clear? And what I'm doing, even very less. Yeah, this one is your theta. This one is your radius, and this is the length of arc. So for this triangle OAB, if this theta is very small, so tan theta is going to be theta, small angle approximation, and that is perpendicular, because for very small triangle, or you can say for very small theta, I need to write properly, for very small theta angle, tan theta is going to be theta, and that is going to be L over R. L is going to be perpendicular over base, right? So we have this relation. So length is going to be R theta. So this is this, and I know V, which is dL by dt, and that is R d theta by dt. Why shouldn't I do dr over dt? Because R is fixed. It is constant, radius of a circle, right? So we have this relation, V equals to R omega. Clear na? What I am doing here, V is the linear velocity, omega is the angular velocity. Then all together we have the three equation of motion for the this omega naught plus alpha t. Here alpha again, differentiate this above equation. This is your equation 2. This is your, okay, this is, I need to rewrite, V equals to dL by dt. Just a minute, beta. V equals to dL over dt. From this relation, we have L equals to theta r. So that is R d theta over dt. And that is R omega. Okay. So this is my equation, or you can say 1 or 2 or anything. Let's say equation 1. Okay, this is my equation 1. Even I teach you this thing, but still I am teaching you again. Again doing differentiation of equation 1. So that is acceleration A, linear acceleration, and that is R alpha. Alpha is angular acceleration, d omega by dt. Clear everyone? Again R is going to remain constant because here R is the radius. So this is your final, or you can say angular velocity after some time. This is your initial angular velocity, that is angular acceleration, that is time. Similarly, theta is going to be omega naught t plus half alpha t square. And the third equation of motion is going to be very simple, that is omega square equals to omega naught square plus 2 alpha theta. So these are the three equations of motion for angular, you can say, or for angular velocity, or for rotational motion. Clear everyone? We have done this thing. I just give you a revision kind of thing. Clear na beta everyone? Mokeshwaran and Anil Dev, what happened to you guys today? Why you kept your camera off? Are you there? Yeah. If you have any particular problem, anything, so you can let me know. If you don't, so please open your camera. Clear? Clear? So that is your motion in a rigid body. Next thing is center of mass. So basically what center of mass? As we already know, rigid bodies are made of components. And even those components are made of n number, or you can say very large number of point mass particles. So finding everything, or you can say finding mass, acceleration, or you can say position vector, displacement, velocity, force, and so for each different particle is the troublesome thing. And that is very time taken, and that is going to be very crucial, or you can say kind of impossible to do the mathematics of that. Clear? So we find a fixed point, or we find a particular point where we assume and where we say that most of the mass of a body is going to be assumed. So for symmetric body, that is going to be very easy, center. But for unsymmetric body, that is going to be a little bit task. So we assume a singular point wherever the maximum, or you can say more than 95% of the mass of an object is going to be situated. That particular point is known as the center of mass. Should I need to write this? Tell me. Definition, because definition is not going to work anywhere. That's why I don't give you. Okay, that is for symmetric thing. As you can see, for ring, that is the center of a mass. For disk, even that is the center of a disk. For rod, that is the center, and that is cylinder, for that is the center, and everything is center of mass, cm. Even for unsymmetric object, okay, what is the meaning of unsymmetric object? Suppose this is your unsymmetric object. Okay, so now assume why this center of mass thing is going to be very important, and what is the role. Suppose I am sitting over here at this particular point O, and not I am, any particular observer. Okay, suppose any observer is sitting over this particular point O. This rigid body, obviously this is a rigid body or unsymmetric body, is made up of, I'm just making very lesser number of particles, don't worry you guys. How much these are? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's make it 10. 10 particles, only 10 particles. Now you can calculate each and everything. If I say I apply an external force on this, I apply external force from here. Okay, so if whatever I know till now, if I'm going to do in this way, so I need to find the 10th different forces due to this external forces, and I need to find 10 different position vectors. Then similarly 10 different velocity. Then similarly, and that is very small. And you know guys, any particular rigid body is not made up of 10 particles only. Why so? Because even one molecule is made up of Avogadro number. What is the Avogadro number? Tell me anyone. What is Avogadro number? And even in an atom we have a different kind of electron, proton, neutron. But don't go up to the range of electron, proton, neutron. We have Avogadro number of atoms in a molecule. Molecule means, for example, H2O. H2O is a molecule. So even in single H2O molecule, we have Avogadro number. What is Avogadro number? Tell me anyone. Do you know what it is? You don't learn this thing in chemistry till now. Avogadro number. How many chapters you done in chemistry? Avogadro is basically a scientist name, and that is exactly. Acha, tell us the correct thing. 6.023 to 10 to the power 23. So if I just pick this H2O, single molecule, one molecule. In this one molecule, I have that much number of atoms. Okay, so I am not going into the depth of atoms. If I just wanted to do each and every calculation of an atom, because atom I can take minute particle, small point particle, so I need to do that much you can say calculation. Now you can think this is all about the for one molecule. If I can take 10 gram only, so that is we have number of moles given mass upon the molar mass. So in 10 gram that is going to be how many number of moles? Molar mass upon given mass. H2O. H2O have 16. Okay. Given mass upon molar mass or molar mass upon given mass? Okay, that is the, suppose 100 gram and 16 is the molar mass. So that many number of moles, even I need to multiply this much also. But I'm saying if I have only 100 gram of water, Okay, so in that 100 gram of water, we have n number of moles, which is 100 upon not 16, that is 18. Wait. H2O. Okay, H have 1 molecular mass and O have 16, so that is 18. That much almost number is going to be the number of moles I need to multiply for only 100 grams. So now you can think of the calculation. Clear? So what I'm going to do, I'm going to suppose I'm going to find an alternate method. An alternate method is, this is my R1, this is my R2, this is my R3, this is my R4, this is my R5, this is my R6, 7, 8, 9, and then 10. So using this, I am going to find a point which is position of center of mass, RCM. And beta RCM is very easy. Every other particle is, okay, wait. R1 to delta, I mean that's R10. So RCM is the center of mass, or you can say position of center of mass. How we can find it? M1 R1 plus M2 R2 plus dot plus M10 R10 divided by M1 plus M2 plus M3 plus dot M10. Basically, I am doing a average thing, and I can say this is this particular point over here is my center of mass. Okay, now now for this particular whole rigid body, I take this whole rigid body as a point mass particle finding the center of mass at this particular point, and I am doing each and everything same given mass upon molar mass. Yeah, and I am doing same everything as compared to the point mass particle. Clear? So that is the story of a center of mass. Is this clear, everyone? Clear na? Because the first thing you're going to learn position of center of mass. Once you have the position of center of mass, we are going to find the what? If we have the position of center of mass, so obviously dividing, or you can say dividing with the time, taking derivative with the time, we can find the velocity of center of mass. Similarly, we can find acceleration of center of mass. So here we are going to do the detailed study of center of mass for discrete thing, for center of mass for continuous objects, and then different objects have a center of mass, and we are going to discuss about it. Then one important subtopic, we have a center of mass for cavity. Cavity is what it is, we are going to discuss after a break. Okay, and then we have a questions, and then done. And then we have a motion of center of mass also, and this yeah, we are not going into the more detail of motion of center of mass.
Excuse me, sir. Sir, I joined right now only. I had a network issue, so.
Amritani.
Yes, sir.
Yeah, it's okay. Yeah, it's okay, beta. Okay. What we done till now, just a quick recap to you. See, this is rigid body of center of mass. We are understand what a rigid body is. Okay, we done the definition of rigid body is motion of rigid body, and then motion, I tell this particular thing, the relation between linear velocity and angular velocity, and the three equations for angular velocity. And you can say the equations of motion for rotation, because in rotation we need to find this angular velocity. And then I am just explaining the center of mass. Clear, everyone? Clear na? So we can move ahead. This is clear? Yes, no? Tell me something, then I go ahead. Na? Clear na, everyone? Just write yes, and if you have any doubt, so you can write it also. Okay. So that is your position of center of mass, or basically in normal book or somewhere you're going to find directly center of mass, but we have this position of COM. Every time I'm going to write COM, it means center of mass. So position of center of mass, first of all we find the position of center of mass of a system of particles. Just to make the subject easy, we classify a system of particles in three groups: system of two particles, system of a large number of particles, continuous body. So these two things basically the discrete one. What is the discrete one? The formula or a subtopic or a theory which I given to you on the last page, discrete body. But you know guys, in real life we don't have discrete bodies. We have the continuous one. Clear na? Okay. So this one is important. You can say more important. Upper two is important because maximum number of times the numerical problem or any particular MCQ you find on center of mass from the continuous body. Maximum number of times. Okay, directly whatever we are going to do here, directly one of the thing you are going to find in your examination. Moving ahead, this is very simple. Center of mass, position of center of mass of two particles. So we have two particles. For example, very clearly you can understand. Suppose these are two particles, two extreme ends. Okay, one particle, another particle. So obviously, if I'm trying to balance from any particular position, so it is not going to be. Obviously, it is going to be balanced in between. Why so? Because it is symmetric. If I make you can say, assume like this: if this end of the particle is very heavy, so the center of mass is going to be shifted a little bit away, because as you can see from the previous relation also, from this the position of center of mass or center of mass is inversely proportional to the mass. So if the left hand mass is the heaviest, so center of mass is going to be shifted here to balance this thing. Clear na? Okay. So center of mass of two particle of masses m1 and m2, separated by a distance d, lies in between the two particles. The distance of center of mass from any particle r is inversely proportional to the mass of the particles. Clear? So that is r inversely proportional to m, and that is m1 r1, m1 r1 equals to m2 r2. So here R1 equals to M2 divided by M1 plus M2D, and R2 equals to M1 divided by M1 plus M2 into D. The D is the distance between them. This is written over here, na? Lies D, I mean by a separation of distance D. Yeah. D is the distance between them. Clear? So that is your one of the important formula. Here R1 is the distance of center of mass from mass 1 and R2 is the distance of center of mass from mass 2. From the above discussion we see that R1 equals to R2 equals to D by 2. Means if M1 by, okay, if this M1, M2 is going to be equal, so this R1 and R2 is going, I mean the center of mass is going to be in between. Center of mass lies midway between the two particles of equal masses. Similarly, R1 is going to be the, I mean major than, I mean this R1 is going to be more than that R2 if M1 is lesser than M2, and R1 is going to be lesser than R2 if M1 is going to be. Center of mass is near to the particles having a larger mass. Okay. One more way you can understand this thing, I can make here. Just give me a little bit time. Suppose this is your origin. Okay, and this is the D distance, and this is M1, this is M2. I need to change the color. Just a minute. This is R1, this is R2. Clear na? This is R2, this is R1. So D is the distance. So obviously, what is center of mass? RCOM M1 R1 plus M2 R2 divided by M1 plus M2. Clear? So from here, if I want to find this R1, so R center of mass M1 plus M2 divided by this. Okay. And similarly, if I want to find R2, so in this case. So this is going to be the D by 2. D by 2 means this is going to be the actual R. Yeah. This point is going to be hit exactly at this midpoint when only and only when means what it is written over here. You can see directly. If M1 is going to be M2. Clear? Then RCOM is, we take M common from the above, R1 plus R2 divided by M, or you can say 2M. So M cancel. So then R1 plus R2 divided by 2. So that is your exact point. This RCOM, which is D by 2, okay, or directly which is R1 plus R2 by 2 for M1 equals to M2 equals to M. Clear? Understood? And in any case, if any of the particle, because the net formula of center of mass is this, formula number 1, in any another case, whatever the mass is going to be larger one. Okay, whatever the mass is going to be the largest, the center of mass is going to be shifted away from this. This is your formula number 1. Because RCM, this is my RCM. So automatically, if this one is large, so R2 is going to be more to make it a balance. Clear everyone? Clear now, beta? So that is the concept of COM or center of mass. Okay. After that, wait. Now we have a center of mass for large number of particles. Large number of particles I already explained to you guys, but again I am going to, don't worry, and that is we have a Cartesian coordinates also. Okay, so that is all about for 2 mass particle, or you can say 2-point mass particle. Okay, moving ahead, this is position of center of mass for large number of particles. Again, large number of particles, what we can think of, I can make this, or the same diagram I am going to repeat. Suppose this is your rigid body, okay, and this rigid body have any access system from there. Okay, just give me a minute. This is your mass M1, mass M2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, so and so. Even I don't know how many these are. Okay, but very large. So what I'm going to do, simple, this, yeah, this one is your 1, 2, 3, okay, and dot 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 nth particle. Clear? Clear na? So as you can see, this one is your M1, M2 and Mn directly. So that is M3. This is R1, this is second one is R2, this one, and this one is R3, and this one is Rn. So again, for large number of particles, we have system of we have a system consisting of n particles of mass M1, M2, M3, and dot 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 Mn. With the, you can say R1, R2 as their position vectors at a given instant of time. The position vector RCOM or center of mass of the system is this. Simple. And you can write in this way also. So RCOM is basically nothing but I equals to 1 to n MIRI divided by total M, where total M is nothing but summation of I equals to 1 to n, I equals to 1 to n, that is M. Clear? That is written over here. Here M is the M1, M2, M3, Mn, and MIRI is called the first moment, or you can say of the mass, moment of the mass. Okay, this is MIRI, MIRI is basically moment of the mass. As we can see, this is all together for three-dimensional thing. This is all together for three-dimensional thing. So suppose we have a center of mass, this. Okay, suppose we have any particular point over here which is a center of mass, a center of mass. So for center of mass we have Ri, which is Xi, Yij and Zik. So in a same fashion, R center of mass is X center of mass on I component, Y center of mass on J component, and Z center of mass on K component. Is this clear, everyone? So this center of mass is a vector quantity, and we say that it is a position vector. So altogether, this either you can write in this way: COM is going to be X COM, I, then Y COM, then J, then Z COM. Is this clear? So that is very easy. Clear na? For X, you can write it down M1, X1, M2, X3, M1, M3, X3, M4, X4, dash, Mn, Xn divided by what? Total M. Okay. If anyone till now is not understood this thing, so that is very easy. X, or okay, X center of mass. Yes, it is very easy. That is, okay, I'm going to write in this way, summation fashion, I equals to 1 to n mi xi divided by capital M. In the same fashion, you can write y. In the same fashion, you can write z. Is this clear, everyone? That is I. MIYI divided by capital M. In the same fashion, you can write for Z. Is this clear, everyone? Clear now? So that is, till now, everything is easy. The things is going to be a little bit crucial or complicated when we are switching into the continuous thing. Okay? Clear, everyone? Na? So that is easy thing till now. Okay, so that is center of mass, and that is your Cartesian coordinate. So XCOM I already given to you, YCM I already given to you, ZCM I already given to you the previous page. So that is easy. Okay, just take a break for 5 to 6 minutes, and then we are going to start this because it takes time. Okay, so we are going to start from this, or you can say there's a 5 to 10 minutes break. And we are going to 10 minutes, so if I'm saying 8:32 start time. And if I'm not coming, so I'm going to be, don't worry. But still, if I'm not at exactly 8:32, so read this and tell me what do you understand from this. Okay, don't leave this class. The main thing is still there. Important thing and important formulas altogether. Hello, 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 hello. Am I audible? Hello, 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 beta. Are you there? Okay, so see, one thing we are going to find or see in every continuous body. See, if it is a continuous body, so obviously we cannot break. What we cannot break? The point. Or because R2, R3, and this thing we are not able to find. So what we can do, we can take a small or very small range of mass, and once we get the small range of mass and we multiply with the x-axis, so we get x center of mass. And if we do into the y-axis, you can see that y-dm, so we get y center of mass. In the same way, we can do that in a z center of mass. Clear? So what is all about, because if it, obviously every continuous body, or you can say any particular continuous thing, is not able to distribute it, or it is not able to, we are not able to describe that with this R1, R2 or discrete system. Um, hmm. Just see, this is, assume this is a continuous rigid body. Obviously it is. So for this continuous, rigid one, rigid body, just within a minute you can understand very easily. I'm not making this axis. This is altogether x, y, and z axis. Okay. So as you can see, this is your x axis, this is your y axis, and this is your z axis. Clear? If I find, where I can do that, here I can. If I make this a very small dm, okay, I take this small section of mass for this whole body, this whole huge body having a mass m, and I take this small tiny piece of dm, and I want to find the center of mass for x, axis. So obviously that is x center of mass. So what I can do, I can make from x axis, so from origin I can draw a perpendicular and so and so. So x center of mass basically is going to be x dm. I integrate this mass over whole thing, and from the x axis I can do that. In the same way, from the y axis I can do that. In the same way, from the z axis I can do that. So what it is altogether a body to have a continuous distribution of matter. Assumption in the formula. So summation in the formula of center of mass is replaced by the integration. Suppose x, y, z are the coordinates of a small element of mass dm. We rewrite the coordinates of center. Okay. So from x axis it is going to be this. Basically, wait a minute. I can do this thing also. This is basically inside, but in general we make this kind of axis system outside. So suppose there is this axis system is going to be, okay, O prime, and that is your z axis. So now for this is your x1 from x axis, okay, this is going to be from y axis, this is going to be the thing, and from z axis, from this z axis, this is going to be the thing. So this is your x, this is your y cum, this is your z cum. So basically different method is going to be used, but here we cannot do the m1, m2, m3 and so on. We pick any particular small mass particle dm instead of summation, because whenever we switch into the continuous body from the discrete body, so this summation is going to be shifted and it is almost equal to the integration from I equals to 1 to n, or you can say from initial to final, and from I equals to 1 to n, or you can say from mass 0 to capital N. Okay, so this method we are going to use. Here dm is the mass of small element x, y, z is the coordinate of C of n of this element. Okay, so this x, y, z is the coordinate of this particular dm. Clear? Means from the x-axis it is going to be this, from y-axis this is going to be this, and from z-axis this is going to be this. So basically this is a coordinate. I mean, this particular point P is in 3D, having x COM from the origin, or y COM and z COM. Basically this particular is going to be the different coordinates. Clear, everyone? Is this clear, beta? So basically, simply we are just going to switch from summation to integration. Okay. Now, the main thing we are going to see in symmetric bodies, for you can say length of a rod of length L of continuous mass, and you can say center of mass for semicircular ring, and then center of mass for this disk system, and then center of mass for you can say in the preceding method, center of mass for rectangular, square shapes, and different kinds of shape we are going to see. Okay, and then after that we have the important thing, that is the cavity. So quickly we are going to see that. So this is the node. In most of the cases, that is the particle. In this case, center of mass of this particle lie over the particle itself. Means in most of the cases, whenever the continuous, or where in most of the cases when we going to take the continuous objects or continuous bodies, so even the center of mass is going to be lie itself the body, or at midpoint, at somewhere another point. Okay, so what it is we are going to see in the next. So that is your important thing. Even the derivation for every class, even the formula. So center of mass for a uniform rod. Uniform rod means the mass is going to be distributed uniformly. Okay, that is not going to change with distance. So suppose a rod of mass m and length L is lying along the x-axis. As you can see, that is lying along the x-axis. Its one end at x equals to 0 and another at x equals to L. At one end we can find, say, we can do this thing also. I just make a origin over there. So this is at x equals to 0 and at x equals to L. So the mass per unit length of this rod is going to be m by L. Clear? If this is the length of the rod, and we can see very easily, the length of the rod is L capital and the total mass is capital M. So the mass per unit rod of the length is m by L. Hence the mass element of PQ. This PQ element, we can take small PQ element of length dx situated at x equals to x. Okay, means this is any particular position from this origin, that is x, from this is dm equals to m by L dx. Basically, the small mass for this length element PQ is mass density into the dx. Clear? This small mass is nothing but mass density, which is you can say m by L into dx, as simple as that. Because dx is the small length and that is your mass density. So that is how we can find dm. Now we can see one important thing. The center of the coordinates of the element PQ are x0, 0. Here, because this PQ, or you can say this small element dx, is lie over the x-axis, so its coordinate is going to be x0, 0. Clear na? So then the x coordinate of center of mass is going to be COM 0 to L x dm and integration of dm. Total mass of this is going to be this. So when we are doing this mathematics, or that is simply XCOM is nothing but 0 to L x m over L dx divided by m, total mass. So 1 by L is going to be 0 to L x dx, and we know this is x square by 2. Okay, XCOM, that is 1 by L x square by 2, and okay, that is 0 to L. I mean, when we are going to put the limits 0 to L, so basically that is 1 by L into L square by 2. So automatically you can see that of any rod of mass, uniform mass m and length L, take this example. This is the rod of mass m, uniformly distributed, and length L. So if I want to balance this thing from one end, so I am not able to. So with the two fingers I can, okay, with the palm even, I can balance only and only with the middle part. If I'm trying to do this one end, so automatically it is going to be false. Okay, and what is the center of mass? Center of mass, or sometimes also known as the center of gravity at a single point, or you can say a point in a symmetric or in any unsymmetric bodies, where we assume the maximum mass or the whole mass of a body is situated, and we can balance that body simply. Clear? So majorly in maximum amount of time for symmetric thing, that is going to be the center of the symmetric shape. For unsymmetric shape also, it is going to be the almost center. Clear na? So that is all about your center of mass for linear length. Okay, related to this concept, there is very important. Related to this concept, you are going to find one important question. Here, as you can see, this mass density is not related or to that length. But to make this question a little bit tricky or a little bit difficult, what we can do, we can make this mass density, which is mass per unit length, is related to x. You can say x squared, something like this. Okay, so when this mass density is related to the x also, or you can say even this, what happened to my eye, x dx, or any particular 2x 3x, okay, not x dx, because dx is over there. So 3x square plus 2 means this mass is all together is changed with the x. So then integration, we cannot put m by L. Simply we need to put this rho, which is 3x square plus dx, and x dx, and multiply x. So the whole integration is going to be changed. Clear na? So the main thing is the mass density sometimes change with the length also. So then the question itself is going to be a little bit changed or a little bit complicated. There you just need to take care of the integration, nothing else. Okay, you're going to find one question at least like this, don't worry. Now the center of mass, because there is no as such thing, or you can say y coordinate is 0, so the y COM is going to be 0. Similarly, z COM is going to be 0, because this particular, okay, one more thing, maybe you can see sometime a length like this also, or you can say a road like this. So now you tell me, what do you going to do? Anyone? And that is very basic question. If there is a road of length L situated like this, so how many COM or center of mass is going to be there? 1, 2 or 3? Tell me. How many? For this shape, How many center of mass you can find? 1, 2 or 3? 1. Why? Why not 2? Why only 1? It is a continuous distribution of mass. One more thing, until unless a fix, that is going to be the applied by the condition. If, okay, one important thing, your center of mass can be changed the moment you can change the origin, isn't it? But I'm saying, if I fix the origin, then it is going to be divided into 2. But I don't fix here the origin. What I'm saying, just focus here. Suppose this is your square. Clear? From this particular point you can understand. I don't fix any particular origin. Any particular origin from the corner is going to be this center. Clear? The center of mass is going to be at the center. But if I am going to say find the center of mass from this point, O. So now tell me where it is going to be lying. Again at the center or somewhere else. It is also dependent on the mass, how how my mass is going to be distributed. But suppose the mass is going to be continuous even for this. So for this O point, it is going to be not center exactly, but obviously then it is going to be this particular point, and this particular point, okay, assume this is the center, but this particular point have 2 points, as you can see over here. Okay, this particular point have 2 points altogether. So we need to find YCM or XCM altogether. Clear na? So the thing is, if I fix a particular origin, or if I fix a particular point, so from that particular point, from that particular origin, the center of mass thing is going to be changed. One thing for sure. Clear? Clear na? Okay. So here, why it is only 1? Because I am not fixing any particular origin. Even if I fix, so I can rotate my axis. Suppose I fix this kind of, so I can rotate my axis little bit. In that scenario, my x-axis is going my x-axis is going to be shifted like this. Obviously, if x-axis is going to be shifted, so y-axis is going to be shifted also. Okay, and then I have 1 only. But if I am stick to this first one only, so then I have 2, x center of mass also and y center of mass also. Clear na? Because then I have somewhere here or anywhere dependent on the mass, but it is again L by 2, but for this and for this I have x center of mass also, I have y center of mass also. Clear? So that is the main important thing. Okay, so now we are going to find the center of mass for different things. First of all, we are going to discuss the center of mass for semicircular ring. Okay, so semicircular ring, just quickly go through this because then we are going to hurry for the cavity ring. So the center of mass for a semicircular ring, figure shows the object. Semicircular ring is this. Okay, by observation we can comment that x coordinate of center of mass on the ring is 0. Why? because we are going to find only on the y-axis. X is not going to be play the role. 0 as half ring is symmetrical about y-axis. I can find x center of mass also for this kind of shape. I mean, if I just rotate my this ring into this, okay, if my ring is somewhere look like this, so I have a center of mass. On the symmetry, y center of mass is going to be 0. Clear na? Because automatically, if it is a ring, if it is a disc, so where I can have somewhere here, somewhere here, somewhere here, somewhere here, only on the x-axis, not even y-axis. It is not going to be, because it is the boundary, and you cannot balance any particular point or assume any particular point on a boundary to balance that particular whole. Simple thing. Okay, logic sometimes. Center of mass of the ring is 0 as half ring is symmetrical about y-axis. So we are going to find the center of mass even x, y, z only and only where the symmetry is going to be. Okay. So I mean the object is going to be symmetric to that axis. So half of ring is symmetric to y-axis on the both sides. Only we need to find the center of mass of y. So for y thing, how you can find it? Simply put any particular point y, and you can say that is r d theta, and that is your y equals to r sine theta. This is your y point na, from x-axis. That is r. Radius of the ring, radius of the semicircular ring is going to be fixed. So this is going to be y, and that is going to be the length r, r d theta. As I told you, tell you in the previous, from the same thing you can get. This length is this r. This L is arc length. This arc length L is r d theta, change in theta, and here y is r sine theta. This is the y. So from this particular formula, we can find the y center of mass, and everything we here dm, we think about an element arc of length at an anything theta. I mean whatever I draw here, the dm and everything is written over here. So dm is rho r d theta. What is this? For this is small, okay, again, for this is small length element, okay, arc length element, which is L. This is r d theta. So I can find dm mass, and this is my mass per unit area. 1/4. Okay. And if it is only ring, so that is going to be mass per unit length. Clear? What I am doing here, for circle I have length 2 pi r. For semicircle I have length how much? Pi r. Clear na? So this is mass per unit length. So here x direction of an angular weight, I mean the angle theta from x direction of angular width d theta, if the radius of the ring is r, then its y coordinate will be r sine theta, and here dm gives this dm rho r d theta. Rho is mass density of a semicircular ring. From equation first, we have y center of 0 to pi. Why 0 to pi? Because symmetry of angle is going to be rotated from 0 to pi only. So that is everything. After this is integration. So from equation first, what is equation first? Y dm divided by dm. This is your equation first, na? And dmy. So put it everything, dm and the value of y. Value of y here is r sine theta. Everything we converted into the this thing, and dm here is rho r d theta. So we are going to discuss. We are going to do the integration in terms of theta and in terms of theta only. So 0 to pi r by pi, 0 to pi sine theta d theta, and this is integration is going to be given to you 2 always. How so? Okay, the guys, the student who don't know I, which is 0 to pi, how much it is? Sine theta d theta, it is going to be, if I'm not wrong, minus of cos theta, value of pi and 0, minus take outside, okay, and then minus 1, that is 2. So note down somewhere, learn if you want to. Don't learn, that is easy. Okay, so this is your note. Means 0 to pi sine theta d theta is going to be how much? 2. If I put cos theta here, so it is going to be 0. Why? Cos theta gives you integration sine theta, and at 0 or pi value, the sine theta or the value of sine is going to be 0. So y center of mass for a semicircular ring is 2r by 5. Simple. Clear everyone? Is this clear now, everyone? Clear? Okay. In the same sense, in the same way, we can find the another things. So that is quite obvious. I'm not going to derive these things. Center of mass for the, proceeding in the similar manner, we can, wait. I can give one thing. I put one more thing in this, but I can't find now. So, center of mass of a uniform circular ring distance at h, which is 2r by 2, 2r by 3. Okay, I am not. See, any other thing, any other particular kind of shape you can find in the same sense. Clear? Okay. Proceeding in the similar manner, we can find the center of mass certain rigid body. Center of mass of some well-known rigid bodies is given below. Center of mass of a uniform rectangular, square, or circular plate lies at the center. So this is your rectangle. This is your square. This is also rectangle. That is also. This is circle. So every symmetric thing have a center of mass at the center. Okay, so this is center of mass of a uniform circular ring, lies at a distance of h equals to 2r by pi from its center on the y-axis of symmetry, where r is the radius of the ring. So we can find out already, this means this is your center of mass for a semicircular ring, that is, wait, we already discussed this thing, so that is not a big thing. Okay, so that is this. Moving ahead, center of mass, uniform circular disc of radius r. Now this is, okay, one change you're going to observe here, how it is going to be for disk, it is going to be 4r over 3 pi. The same thing you need to do, but here the mass density is going to be related with area. It is a disk, na? What is the meaning of disk? This mass is also there. This is also there. This is covered fully. So if it is covered fully, so linear mass density, it is not going to work it out here. What it is going to work out here? Surface mass density. And what it is? Pi r square by 2. Okay. When you can put this, and any particular value, again symmetry on the y and everything the remaining same, y dm divided by m, but you just need to put this instead of I mean dm is going to be in this small case. Clear? This and area. So automatically you can find the same thing. Center of mass of hemispherical shell. So hemispherical shell is going to be at the center, which is r by 2. Okay, means if it is a shell means it is hollow. Hemispherical shell, or you can say hollow sphere, hollow hemisphere, same thing. So if it is a hollow hemisphere, so again we can do this, that is mass per unit length, and that is what? Mass over what it is? Pi r for radius r. For hemisphere of radius r. Hemisphere of radius r. Same everything you need to do, and you can find automatically that is r by 2, center of mass. Okay, so here center of mass is going to be h, which is center of mass, it is going to be r by 2. Clear? That is the scenario, that is the case. For solid hemisphere, that is again it is going to be 3r by 8, and the same thing you need to do here. Mass per unit radian, that is 2 pi r square, because hemisphere, it is a hemisphere na, so sphere have 4 pi r square and that is have 2 pi r square. So we need to do this and automatically you can find the answer. Clear everyone? Now this is the important thing and that is the main thing. Or you can say very important. See, what is cavity first of all altogether? Cavity is a hollow space, if we cut it out some part and the remaining part we need to find the center of mass. As you can see in this diagram, this is the whole, okay, this is the whole, you can say full sphere, or in this particular full sphere I cut it out this small sphere, but when I cut it out, so I want to find the center of mass for this remaining thing, and the remaining thing beta is this. Remaining thing is this thing. Just a minute. I have only this shape now, the red dotted part. Okay, just okay, and this yellow part is going to be taken out. So I want to find this remaining red dotted part, I can say region 2, center of mass. So how can I do that? That is first of all known as cavity. Clear? Okay. One simple thing you can understand. How you can understand more clearly? Suppose there is a square, and from this square I can take it out this small circle. Now I am going to say find the center of mass for this shape. So how are you going to do? Obviously in the same manner we are going to find the center of mass for the square. First of all we are going to find the center of mass for the square. For the square first of all, then we are going to find the center of mass for this particular circle, but circle is taken out, so we are going to subtract this. Clear na? What is cavity in all together? This piece, this circular piece is cut it out and taken over here. Clear? So that is all about cavity. Okay. So to find the center of mass, what we are going to do? We are going to find the center of mass for whole thing plus negative. Why negative? Because that is cut it out and taken out. Clear na? So that is the actual, you can see that center of mass for the cavity. Is this clear, everyone? The cavity thing, because cavity thing you are going to see. Is this clear with everyone? Is it clear or not? The cavity thing. Clear, everyone? Clear na? So for a cavity part, whatever the cutout part, we can take at that particular part as a negative of center of mass. Simple. Or the center of mass for that particular particle, for that particular shape, not particle, we taken as a negative thing. Okay. So just a minute. So what it is written over, first of all, cavity, what it is. If some area is removed from the rigid body, then the position of center of mass remaining portion is obtained by assuming that the remaining part is positive mass and negative mass, which is there. Further steps are explained in this example. To find the center of mass of truncated bodies or bodies with cavities, we can make use of superposition principle. That is, if we restore the removed part in the same place, we obtain the original body. The idea is illustrated in this. Okay, if we put it this particular cavity part, so we can get the same thing, the whole actual body, but it is already removed, so we can take this thing as a negative and this thing as a positive. Or this is the whole thing. From the whole thing positive, if we take it out, if we subtract the negative thing, so we can get the cavity. Clear? Means this is the cutout part plus the remaining part, and I want to find the center of mass of this. Center of mass of this. So this is the whole center of mass of the actual body minus this can shift here. Okay, and if it is shift here, so this is all about the center of mass of this. Control Y. Wait a minute. Then this is the origin. We can say axis system. Then I can do this here. Okay. If it is, I mean, obviously it is going to shift there. So this is the center of mass for the whole body. We can take positive. If I not X only, RC. And that is negative of RCOM for the cutout part. And when we do this thing, so we get this remaining part or center of mass of cavity. Is this clear? Cavity. Okay. So we are going to see this thing in the next page. So the removed portion is added to the truncated body, keeping their location unchanged relative to the coordinate frame. That is simple theory. If a portion of a body is taken out, the remaining portion may be considered as original mass minus the mass removed of the part small m. So that is going to be original mass plus minus of the mass of the removed part m, and the formula changes to x center of mass is capital M x minus small mx prime divided by m minus, where x prime, y prime and z prime are the coordinates of the center of mass of the removed part, and that is your actual center of mass for the cavity. Clear? Is this clear, beta? So basically, just find the center of mass for the removed part, find the center of mass for the whole body, and subtract that. You can get the center of mass of the cavity. Okay. So this is your first question. As you can see here, your mass density is related with x. Clear na? I give you a hint. Do this. Find the position of center of mass of this row. Do this. The same thing what you done in the previous, but here this row, I mean the mass density is not simple, it is related to A plus B into X, and the length is going to be L. I mean this equals to change its initial thing, it is going to be lie in between x0 to x equals to L. Okay, the linear mass density, mass per unit length, is varies with distance x. So you need to find the answer of this, and that is one of the important, or you can say most again and again coming question, like in every year, in after 1 year or 2 years, you are going to find questions like this. Okay, do that quickly. After this, we have one cavity related question, and then we have motion of center of mass, and then that's it. Motion of center of mass question are not going to be asked, are not given to you guys, just what it is, we are provided that. And then we need to do this thing, which is what it is, class assessment also. And I need to check your class assessment is done, but I don't think so your homework is done. Do this quickly. Or should I tell you the whole? If you want to discuss the full, let me know here. I want you try guys by yourself, at least initial starting thing, and then I'm going to tell you obviously. Assessment, this is this. Okay. Class assessment is already there, and homework I need to put. Just give me a minute. There is this, there is this. Control. Okay, homework you can do at home. Chapter is this. Add it to the course and done. Homework is also done. Class assessment. 2L by 3 by 0. I got it. Better that is not that much easy. Okay, see. I think I need to tell you. Or you guys are doing? Anyone? This is not the correct answer. Anil. Better this row mass, linear mass density is already dependent on x. Wait. Here, okay. Might be, Beta, you get this answer wrong. Why so? Because this is also mat type. Sorry, my bad. This is a plus bx. Now try. Okay. You do the correct thing with the integration, but this is this. Okay. Hint. Rho here, which is linear mass density a plus bx. Okay, and obviously you need to find x center of mass only and only. So the integration is going to be a little bit changed now. Okay, I can calculate for you guys, the students who are not doing. See, this is the all the cases are going to be remain the same. There is a rod of length L. You need to put length element dq of length element pq of length dx and mass dm. The only change here is rho. is going to be A plus B into X. So dm is going to be rho dx, and that is going to be changed. Simple. The center of mass of the element has coordinate x0, 0. Therefore, therefore the center of mass of the rod will be xcom, 0 to L xdm, 0 to L dm. You need to calculate this dm altogether. Okay, so when you do this integration, you get this 3al plus 2bl square by 6a plus 3bl, and so and so. So y coordinate, z coordinate is going to be 0 because there is no as such at y, there is no as such at z. So this is the center of mass. Either you can write x center of mass, or either you can write center of mass in simple way. Clear? And the next thing, this is a disk of radius r is cut out from a uniform thin sheet of metal. A circular hole of radius r by 2 is now cut out from the disk, with the hole being tangent to the center of the original disk. Find the, with this hole being the center of the original disk, you need to find the center of mass for this cavity. The center of mass you need to find with this thing. For simplicity, I can give you the diagram of this. This is how somehow look like the diagram. To make a little bit clear, this is how your diagram is. Means a whole disk R. From this whole disk R, the circle or a disk of radius r by 2 is taken out, and you need to find the center of mass. So you can see the distance moved from the center of mass. Clear? Is this clear? Or should I explain? See, I need to, I think, because time is running. See what it is. We treat the whole as a negative mass. The object is combined with the original uncut disk. When the two are overlapped together, the whole region of the zero mass, by symmetry, the center of mass lie along the y-axis. Okay. In figure, so x center of mass is going to be 0. The origin and the center of the original circle, whose mass is assumed to be m. The mass of the original uncut circle is m1 equals to m, and location of center of mass is 0 somewhere. X is going to be minus r by 6. Exactly. Okay. So mass of the whole of the negative mass is m2, which is m by 4, and location of the center of mass is r by 2, because for the center, for the you can say circle of radius r, we have this r by 2, and y of center of mass m1 y1 m2 y2 divided by this, where m is 0 minus m by 4, m2 is minus m by 4, is going to be r by 2, and doing this calculation, that is minus of r by 6 from this. So the distance required is r by 6. Okay. Now, once we know the this center of mass, so the motion of center of mass is very easy, and you are not going to get motion of center of mass for continuously. One thing is make me easy for you guys. So if you know center of mass m1 r1 m2 r2 and so, so just do the derivative of this. So velocity of center of mass is dr by dt, which is dr by drcom by dt, m1 dr1 by dt, m2 dr2 by dt, m3 drt by dt. So basically this v of center of mass is m1 v1 plus m2 v2 plus dot mn vn, obviously plus over there, is going to be m1 plus m2 plus dot plus mn. Clear? center of mass is going to be in this way. I already explained in the previous page. In the same fashion, acceleration of center of mass runs automatically. I mean, again, when we differentiate the velocity of center of mass, so we get acceleration of center of mass. Nothing as such more. So this is done. You have 6-7 minutes. You can use 10 if you want to. Okay. So summary. In introduction, we do the rigid body and center of mass. Motion in rigid body we understand. Center of mass in a great detail we understand. Motion of a center of mass we already done. Okay. So now this is your what it is, class assessment test link. I don't like this color anymore. So this is your class assessment test link. Click on this link, open your test and do that. And if you find any particular question I need to describe, let me know. Okay. Meanwhile, as usual, as I already tell you, homework is also important. Okay, homework is also important. Complete that too. Wait, yeah. Okay. I am there, just open this test, and if you find in any particular difficulty and so let me know. Where is this your assessment? In this particular chapter we have this, and this is your this, and this is your this. Okay, so we have 6 questions if I am not wrong. Each particular topic I already teach you. First is very easy, second is very easy, third is subsection region, fourth is easy too, fifth and sixth you need to think a little bit, nothing more. So do that, and if you still find anything that is not understood to you guys, let me know. Okay. Meanwhile, I need to check something. I'm here, I'm just looking at you. Just do this test as soon as possible and obviously take your time, 10-5 minutes. But I think that this particular test doesn't take more than 10 minutes. Is there any question you want to ask, you want to discuss? Tell me, beta. I assign class assessment as well as homework. If you want any particular question here, I mean, if you want it, so I can discuss, but I don't think so. And don't think what I think. Just ask if you want to. Tell me, in the fifth question, if you are confused, so it is a disk removed. Okay, and take this particular thing, which is surface mass, like surface charge density. So the mass density is going to be surface mass density. Clear, everyone? 1, 2, 3, 4, 5, 6. Is this clear, beta? Netra and the new student Anushika. Are you there? Okay, Shuram, Bhuvna, everyone also. Completed. Okay, beta. Okay, so if you done, so we can end this class. Thank you for your cooperation and patience and everything. In the next lecture, we are going to talk about the torque and angular momentum conservation. Okay, clear?